Good afternoon. Thank you so much for attending this seminar. Today, we are glad to introduce Dr. Faisal Alamgir, a recognized professor from the Georgia Institute of Technology. Dr. Faisal Alamgir joined the Georgia Institute of Technology as an assistant professor in the School of Material Science and Engineering in the fall of 2007, and he was promoted to associate professor with a tenure in 2013. He earned his bachelor degree in physics and mathematics from the Coe College and his PhD in material science and engineering from Lehigh University. He held a postdoctoral position jointly between Brookhaven National Laboratory and Hunter College of the City University of New York, and a simultaneous position as adjunct professor at the CUNA Hunter College, where he taught physics courses. In the 2006, he joined the National Institute of Standards and Technology as a visiting scientist to develop experimental capabilities at the Hard X-ray spectroscopy beamline at Brookhaven National Laboratory and served in that position for 1.5 years. With that, I ask that you give your full attention to Dr. Alamgir and please welcome him to this talk. Please, Dr. Faisal, you can start your talk. Thank you.
Let's go. Thank you again, Liliana, and thank you to all the students who are here. Let me just start by quickly introducing my department at Georgia Institute of Technology. Just a little bit of the history of the department. You can see from this list, this timeline, that the department is a little bit more than 120 years old, and it essentially used to serve mainly the textile engineering, and then later ceramic and metallurgical engineering. And then there were two separate departments, actually. There was the textile side, and there was the more hard materials side. And all of that eventually merged in 2010. And so 10 years ago, we had a merger and we became one of the largest material science departments in the country, in the United States. A little bit more about us. We have in the order of 500 students attending at any one time. That includes about 300 undergraduates and about, in the order of 200 undergraduates. Nowadays, or in the last year, I think it was a little bit short of that. We are serving about 37 or 38% women scientists and engineers, and we our ranking among public universities in the United States is #1 for undergraduate and 4th among in the graduate programs. For my presentation today, I'll be referring to some papers, work that you could find on the list on the left that would be directly relevant to what I'm presenting, and some related papers which maybe don't directly I'm not going to directly address, but they are part of the body of work that led to the kind of topics that we'll be talking about today. So I'm going to get right into it without too much delay. I'll go right into the technical aspect of it. So this is going to be a talk about catalysis. However, in a moment, we will see that the idea behind the design of this type of catalyst material actually can be applied to other types of materials. So we will see that soon. Let me take this opportunity to bring a laser pointer up. So you should be able to see a laser pointer. Liliana, if you could confirm that you can see that on the screen.
Sorry, Professor, I cannot see.
I
Yes,
think there
now.
might be a small delay. Okay, so you see it now?
Yes, Professor, now I can see.
Yes, thank you. So I think there's at least a 5-second delay between what you're seeing on the screen and what you're hearing. So I have to be aware of that when I present. So you may or may not be familiar with this concept of a Sabatier principle. And I can discuss it in terms of what in the United States or in the English-speaking world, we have this children's story about Goldilocks. I don't know if there's a parallel one in Mexico. Goldilocks is this this little girl who happens to go into the forest, and she comes up on this cabin, and in the cabin she finds three of everything. She finds a chair that is too big for her, and another chair that is maybe too soft for her, and then finally she finds the right one that is optimal. So she goes through the whole house and tries different things out, and she finds that there's always one that is too much on one side, another one that is too much on the other side, and there's a third one which is perfect, which is optimal. That is kind of what the Sabatier principle is about. So there's an optimal, if you look at, for example, catalytic activity, and you look at whether or not a material is bonding to, when you have a catalysis reaction, you have to have reactants that bond to the surface of your catalyst. And what you want for that catalyst is you want the reactants to bond, but not bond too strongly. Right, so you want to make sure that there's sufficient bonding so that you can actually promote the reaction. But if it bonds too strongly, then it slows down the reaction. So there is an optimal bonding strength. Now, when you look at a reaction like the one that's highlighted here, this is the multiple steps of the so-called oxygen reduction reaction. That is a very key reaction for a fuel cell. In that oxygen reduction reaction, you find that there are different types of catalysts that we could be using. And this is a schematic, but the data points here are based off of this paper by Norskov back in 2004. And for this oxygen reduction reaction, we could try different catalysts, and we can see that if we try something like nickel or iron, then the oxygen absorption part of the reaction is too strong, and so we cannot, the reactants don't absorb fast enough. On the other end of it, if the absorption is too weak, then we don't have sufficient activity for the material. It turns out that one of the best catalysts for the oxygen reduction reaction is platinum, and this is just in comparison to the other pure metals, but it later was discovered that some alloys of platinum with other materials can actually be even better. So the issue is that this alloying, if we actually want to have platinum combined with another metal, then that automatically incorporates two effects. It incorporates the charge transfer effect, that is the amount of electronic coupling that's happening between platinum and, let's say, the supporting material, supporting metal, or the alloyed metal. That's what we would call the ligand effect or the electronic effect. But together with that, there's the strain effect. That is, if you put material like iridium here with platinum on top, then because of the mismatch, the lattice mismatch, you're going to have slight compressive strain on the platinum, because the iridium atoms on average are a little bit smaller than the platinum atoms, and in order for the platinum to bond effectively with the iridium, they have to be squeezed together a little tighter. Alternatively, if you put gold as a substrate material and grow platinum on top, then you have the opposite effect. You have a tension, and that tension would essentially be pulling the platinum apart a little bit. So if you look at the effect of these tension or compression, you find that the electronic band, the D band, which is the relevant valence band for the platinum, essentially can move up and down relative to the Fermi energy, and that has consequences on the chemical reaction. So if you put compressive strain, then it moves away, versus if you put a tensile strain, it moves closer to the Fermi level. And when we're saying it moves, we're talking about, let's say, the center of mass of that band. So the effect of that actually is that it affects both, or it affects all parts of the oxygen reduction reaction. So they're not the same effect. So you can essentially get a compression can induce a weaker adsorption and less efficient bond breakage. However, it can make it easy for the desorption to take place, so that you don't get a poisoning of the surface. However, if you have a tensile strain, you have a stronger adsorption, which may end up being a weak link if it's too strongly bonded. But when you adsorb this oxygen, it also makes it more facile, more easy to break the oxygen-oxygen bond, which means that as you adsorb, you immediately would be breaking the bond, which would mean that you could move to the next step. The next step would then be the desorption of the OH, and in this case, it is a little more difficult. So neither of these two on their own is optimal, and that's where the electronic effect can play a role. So you can see here the effect of the different types of substrate material on platinum. If platinum is the capping layer, monolayer platinum on different types of substrate materials, the same type of Sabatier principle can be applied. And we see in this case, the best one seems to be one where you have a slight tensile strain on the material. And this is actually contrary to, if you look at, let's say 5, so if you look at platinum on platinum, it's essentially it gives a little bit better performance if you have so if you look at palladium as the substrate, the palladium seems to want to squeeze the platinum atoms a little bit tighter because palladium is a little bit smaller. So I misspoke a little earlier. I said tensile, it should have been compression. So when you have palladium as the substrate, it applies a compressive strain on the platinum, and that compressive strain seems to help. So that's something to keep in our minds. Right. On the other end, if you're looking at catalysis, the issue is often not really just about the activity of the catalyst. The activity of the catalyst is what we've been describing so far. How efficient is it in doing the reaction that it needs to do? The other part of a practical catalyst is that it also has to be stable over many cycles of that reaction. And in the case of these catalysts, the idea that has been fairly integrated into applications by now is that the size of the catalyst matters. The smaller the size of the catalyst, the larger is the surface area to volume. And if you have a large surface area to volume, then you have a large effective reaction surface. The way to achieve this is to obviously break the particles down into as small a size as possible. So that's where a lot of work has gone into trying to design sort of stable catalyst particles that are as small as possible. Now, what also happens is that when you make them very small, then they're kind of in a metastable state. For example, if you have a nanometer sized or 2 nanometer sized particle, as you have the reaction happen over and over again, what you're going to incentivize is for those particles to kind of migrate, or atoms from those particles to migrate and start to grow one of the particles at the cost of others. In other words, you can have an effect called ripening right here. You could also have the catalyst atoms, because the particles are small and the surfaces are very reactive. The reactive surfaces also makes it easier for the catalyst to kind of lose itself, corrode, right? And so you can have, taking the example of platinum, you can have platinum dissolution. There can also be physical detachment, right? And the support material itself can actually start to degrade. And finally, you can have particles combine and start to grow, not just through ripening, but through agglomeration. So all of these are kind of effects that over time will lower the effectiveness of the catalyst by not making them stable enough against change. Catalyst has to resist change. That's one of the big prerequisites for a catalyst. So finally, one of the things that you could try to do is, as we just discussed, is to tune the catalyst activity by alloying a second metal, a second material. So in this case, platinum can be alloyed with several other metals, and therefore you can try to get better activity. But the problem there is that the relative activity of the different elements over time has an effect of changing the composition of the catalyst. So in other words, for example, in this case, if we had iron or cobalt as one of the second elements, over time what you would see is that the cobalt is corroded away, and you'd be left with a shell of the platinum only. Or you could try to put the platinum, for example, just as an exclusive surface layer, but even then you could have over time hollow out the particle, because the element that's more reactive on the inside can over time leach out. Not more reactive for the catalytic reaction that you're interested in, but more reactive from a corrosion reaction point of view. Anyway, all of this got us thinking, why should we try to make things three-dimensional? Three-dimensional particles, these nanoparticles, have a lot of inherent problems. You have, first of all, you don't know what you have. You have things that are described as an average, right? You have an average number of corners, an average number of defects, an average number of edge sites, and an average number of the different types of facets. So you can only study things systematically up to a point if you have particles, because you have to be able to control those particles' shapes, their defect concentrations, their sizes very, very carefully in order to do any systematic study. So the problem that we noticed was that a lot of the understanding about catalysis was coming from studies that were not being done systematically enough. And there was a lot of kind of pseudo knowledge that was out there. And so people were sort of getting a sense of what works and what doesn't, but they didn't really understand why. And part of the reason is because they were always working with three-dimensional particulate catalysts. So from a study point of view, it seemed very intuitive for us to go to two-dimensional catalysts. That is, if we could make sure that the catalysts are at least flat, then we can study the effect of, let's say, one of the dimensions. Just by making the catalyst thicker, we could try to see how the number of layers of the catalyst affects the activity. Because the larger the number of layers, the further the surface layer is from the substrate. So that's one effect. And the 2D rendition of the catalyst allows us to do that. The second effect we could study is the strain. So the further away you get away from the interface with the support, the lower is your strain, potential strain, as long as you have epitaxial type of matching between the lattice of your catalyst and the lattice of your support. So what we decided to do was to try and simplify the problem by going into pseudo epitaxy between the support materials and the catalyst materials. This way, we could study the transfer of charge, we could study the transfer of strain, we could try to study them exclusively from one another, and we could then try to design tuned properties by designing the architecture. So there are some other advantages here. Now, if you could make the support material be a two-dimensional material to begin with. So for example, graphene, if graphene was our support material, then we can imagine that you can tune the property of the catalyst that you grow by having a different metal or different material on the other side of graphene. From the other side of graphene, through charge transfer, you can influence the catalytic properties of your platinum, let's say, that you have on the other side of the graphene. So that's an electronic effect that you can control by choosing the right material below the graphene support. The second thing we could do is you could control the strain on the platinum by the graphene. The graphene itself, as long as we could figure out whether or not the graphene actually transfers strain on the platinum or not. In other words, can we grow platinum as a film on graphene? If we can, then the strain condition would come from the graphene. And if the strain condition comes from graphene and is locked in by graphene, then that would be separated from the charge transfer effect that you could control from the other side of graphene by a different material. So in other words, we could do strain engineering on the one hand, and we could do charge transfer engineering along another axis. So that's one effect that we could try to pursue. Now, this kind of idea could have other applications. So one of them is magnetism. So this is a little bit off topic here, but we're thinking about the fact that when you can make metals into ultra thin films, it is possible that this quantum confinement would push the metals under these conditions, under these low dimensional quantum confined conditions, to have different to satisfy different criteria for magnetic properties, for example. So here is a so-called Stoner criterion that, just to put it very qualitatively,
Dr. Alamgir, I'm sorry, I don't know if it's my internet, but I cannot listen you. I'm sorry, some of the attendees can indicate me if the problem is my internet or is the connection of Dr. Alamgir, please. I'm so sorry. I think Dr. Alamgir has a connection problem. I will connect him in brief. Thank you so much. Hi, Dr. Alamgir. Can you
Yes,
listen to me?
yes.
Okay. Thank you, thank you. I think some problem in the connection.
Okay, let me start sharing again.
Thank you.
Okay, do you see it?
Yes, now I can see, but yes, now.
Okay.
Thank you.
All right. So just in the interest of time, since we lost a couple of minutes, let me just continue. I was just going to say that using graphene as a support material, you can control various quantum confined effects, and some of those are being described on the right over here. But I will skip them for now, and I'll come back to them if we have time later on. Okay. So I'm going to skip this part on the right. So what we do is we grow atomic layer films of these catalysts by using a method of layer by layer deposition. The acronym here stands for surface limited redox reaction, SLRR. And by the number of cycles of this, you can essentially control how many layers of platinum we are growing. Can you hear me?
Yes, we can
Okay.
hear you.
All right. So then, as a way to kind of investigate the chemical effects, we use the ORR reaction, the oxygen reduction reaction that I described before. And we are going to use this method called linear sweep voltammetry, where we sweep down from the oxidative potential and towards the reduction potential, and we will look at the onset current of these reduction at the reduction potential. So that's kind of a standard way of measuring the activity, the electrochemical activity of this catalyst. One thing we noticed as our early study was that as a function of the thickness of the catalyst, we can control the chemical state of the platinum. This is a little bit busy, so let me spend a minute explaining what we are looking at. This stack of plots is for X-ray photoelectron spectroscopy, XPS. And I presume that you've heard of this technique, or maybe many of you have even used it. It's a surface technique, X-ray photoelectron spectroscopy, that allows you to look at the binding energy of the different elements that are present at the surface. And by using the binding energy, you can identify which element it is, and you can find out what the chemical state is. So here we're looking at, if you look at this legend here, we have the samples that we're studying are 0.3 ml, ml stands for monolayer, 0.3 monolayer, 0.6 monolayer, 1 monolayer, and 2 monolayers. And so that would be these here. And we also have one that's called spont, that's for spontaneous. The spontaneous means that we just dip our substrate into platinum solution, and we just pick up whatever platinum comes on, onto the substrate. without an electrochemical reaction. That is, we're not essentially, we're not reducing the platinum electrochemically, we just pick it up. Compared to these 0.3, 0.6, 1, and 2, those are done through this SLRR or electrochemical reaction. What we notice is that very quickly, what we notice is that in addition to metallic platinum, the metallic platinum would be given by this band of yellow. In addition to the metallic platinum, we also have these other peaks that represent cationic platinum. That means we have, in addition to platinum's metallic, we also have ionic platinum, and only after you go past one monolayer of platinum do you start to have the metallic nature of platinum evidenced. Okay, and that kind of makes sense intuitively because you need the metallic bond to be able to form, and in order for the metallic bond to be able to form, you need to have kind of a continuous layer. So at least a 2D layer of platinum is needed to get that. And my screen seems to be stuck. Sorry about this.
Don't worry, Professor. Sorry, Professor Alamgir, can you help me? Okay, I think some connection problem is happening. Please, I ask for please stay some minutes. We will wait for Dr. Alamgir. Thank you so much. Yes, Dr. Alamgir, can you hear me now?
Yes, I can.
Okay, thank you.
What was the last thing you guys saw?
The last slide was transition from cationic to metal ions, I think.
Okay, all right. Let me try now. Okay, do you see the presentation?
Yes, now I can see.
Okay. All right, so let me again skip a slide and get to the result of that earlier study. And the result of the earlier study is expressed in this cartoon, where we see that when you are less than one monolayer thick, then you have cationic platinum. That is platinum that is chemically bonded still to the nonmetals in kind of an ionic bond, and you have these molecules of platinum, platinum molecules stuck to the surface, and they're not very active for the catalysis. And then when you get to one monolayer, you still have a bunch of these molecules still present, and it's only after you get past two monolayers that you have a fully evidenced early on. Started to start interrupting the interface between the support and the catalyst by introducing a layer of graphene. Now, the layer of graphene could be in between the catalyst and it could be the support itself, having kind of a support of choice below. So this non-identified support material down here can be whatever you want it to be. The ultimate support could be whatever we want it to be, or we could have a support that we choose ahead of time grow our platinum, and then we use graphene as a capping layer. That means we try to see whether we can do a reaction through graphene. And then we could try to also sandwich platinum in between the two layers of graphene. So all of this work you'll find in the different aspects of this work in the papers that are highlighted here on the right. Okay, so first thing we needed to look at was if we used graphene on the top, then can we actually have a reaction through the graphene? And what we're doing here is we're comparing in the black and red, we're comparing 4 monolayers of platinum that are grown on graphene, and we are seeing how different is that linear sweep voltammetry as a function of whether or not we have graphene on top. And we can see that here we can see the derivative of that ORR reaction, and here's the actual reaction itself, that they are very similar to each other. And so we are able to drive the reaction through in both the overall current and the position, the voltage at which it occurs. Both of those correspond fairly well, whether or not we have graphene on top. So just to summarize this page, we just wanted to check first whether or not a reaction that we normally could do with these monolayers of graphene can still be done if we put graphene on top of it and run the reaction through the graphene. All right, so if we can do this, then as we've just demonstrated, we can essentially have a dual role for graphene. We can use it as a cap, and we could use it as a template for growth. So we could either use the graphene as a template for platinum growth and transfer some specific strain through epitaxy, and we could also use it as a cap and try to use it as a protection against corrosion. So it could affect our activity, and it could affect our stability. So the first question that we have to ask is, do we actually have kind of an epitaxy type of structure? And when we look at our material under a TEM, high resolution TEM, what we found is that indeed our graphene lattice and our platinum lattice are matched up such that you have the platinum atoms are in a pseudo 100 facet, and that 100 facet allows it to essentially occupy these in one direction it would be the armchair positions of the graphene, and along the other direction it would be the zigzag positions of graphene. And occupying those positions, you end up getting a square-like lattice, or the 100 lattice. What we later found was that the activity and between the templated case and the non-templated case are very comparable to each other. The first thing is that we wanted to compare the activity and stability of these templated graphene templated platinum monolayers, and compare them to the non-graphene templated cases. And we find that the overall behavior is very similar between the two cases. So on the left here, you can see the plots here. You can see on the left panel, you will have the GR stands for graphene. So whether you have graphene as a sandwich in between platinum and gold or not, the overall behavior as a function of the number of monolayers is very similar. Okay, so that's just something to keep in mind. Now, you also are able to induce the strain from the graphene, and you can see that using X-ray absorption spectroscopy. I apologize that this font is a little large, and it's covered up a little bit. But we are able to get this compressive strain, and you can see that compressive strain by looking at the nearest neighbor platinum distance, and it's a little bit shorter when we have the graphene templated, beyond the monolayer. What is the effect of this? The effect of this is that we are able to decouple the electronic effect, which we can follow along with the XPS peak position or the ORR voltage, when we have graphene in between. So if you look at the blue curve here, the blue curve is without any graphene present. And down here, you also have the blue curve, which is without any graphene present. What we're seeing down here is the XPS peak position, that is the actual chemical state of platinum and how that is affected by the number of monolayers. And that is just been basically measuring the electronic effect. And the electronic effect or ligand effect is directly influencing my ORR current. So blue to blue is very highly correlated. But the moment we have the graphene, we lose that correlation. Now you look at the ORR effect and we look at the XPS peak position, and they're not directly correlated to each other. So now we introduce a strain effect coming from the graphene, and it interrupts this behavior. What about the stability? When we have the graphene as a sandwich, it increases our platinum retention quite noticeably. You can see that when you have 3 monolayers of platinum on graphene and more than 3 or more layers, we essentially, after 1,000 cycles, retain about 70% of our catalyst. Whereas same 3 monolayers without the graphene, we lose nearly 50% of our catalyst. So that's just one case. But what if we have graphene as a cap? That is, graphene is the top layer, and it is put there intentionally to protect the platinum. In that case, first of all, we needed to see that we had a similar kind of effect where we could correlate the shift in our ORR potential to our platinum binding energy. And at the same time, we could see that compressive strain. So those two things are telling us that there is an epitaxial relationship between the graphene that you put on top and the platinum that it's interfaced with. And when we do the reaction studies over multiple cycles, here's a key result. When we look at the upper panel here, we see this, what we see here is 1 to 4 monolayers, but this is for the cases where we do not have any graphene cap, the upper panel. So this is just platinum monolayers. The lower panel is platinum monolayers, but with graphene as a cap. Are you guys, can you guys hear?
Yes, Professor, we can hear you.
Okay, all right. I just heard a beeping sound, so let me continue. So if you look at the platinum and gold peaks here, what you see is that after 1,000 cycles, the gold peaks, which are below the platinum, that is, the gold, the material gold is supposed to be covered by the platinum, and after 1,000 cycles, if the platinum is being washed away, the gold starts to be evidenced again, right? And so we see that the gold is starting to peak up here. Let me use the laser pointer. Peak through here, here, we can see the gold peeking through. But if we had graphene as a capping layer, essentially we lose no platinum at all. So this is a very key result. The question then is, are we sacrificing activity when we do this? Because if we are getting a very high stability, but we actually do this at the cost of very low activity, that wouldn't be really useful. But it turns out that that's not the case. We have the full activity of the platinum catalyst that we expected without graphene. So if we had no graphene, the amount of activity we would have expected, we have essentially the same activity when we have the graphene on top. I already showed this before, but I just wanted to remind you again that this is true not only for that one case that we showed before, but also for 1 monolayer, 2 monolayers, and 3 monolayers. And what I showed before was for 4 monolayers. There's the same activity at the beginning, but over time, the activity for the case where the platinum is not being capped by a graphene drops off very fast, whereas the activity for the graphene capped case is retained. So we just wanted to make sure that this is real epitaxy. And so when you look at it over large regions, we see that yes, it is epitaxy, and you can see the atoms decorated all the way. If you're lucky enough to find these regions where you can see the last line of atoms, you can see how they're decorated. You can see defects like this is a dislocation right here. You can see individual platinum atoms in what I presume are defect sites on the graphene. You can see 1 layer and 2 layer thick platinum. The fact that it's 2 layers thick is something that we explored here on stacking. When we played with the contrast, what we can see is that this region is actually 1 layer thick, and the region next to it is about 2 layers thick. And then we also have those individual platinum atoms on the second layer. What we are basically saying is that the stacking is such that the 100 stacking is retained even into the second layer. We'll see more of this from different regions, and we can see that the regions are fairly large. Let me move this bar here. So you can see that this is a region that would be in at least 100 nanometers squared, if not more, and that region is continuously covered with platinum. So it is a film. It's not nanoparticles. Then we can see if you're sitting with the microscope, then the energy from the electron gun of the microscope actually drives reaction. It drives a rearrangement of the platinum, and we can see, for example, here, as we sit there, we can watch the platinum atoms come in and form this film. And we can see platinum atoms migrating under different conditions here. And this is actually platinum atoms going across what looked like a thin layer of amorphous carbon. And at large enough thickness, when we start stacking up until we get the third layer, we start to see triangular arrangements start to emerge. Although they're not perfect triangles, we start to see this hexagonal arrangement, or kind of 1-1-1 type of reconstruction happening. All right, all this led us to then do some investigation on the computational side. We wanted to know whether the 100 platinum, how stable is it against platinum dissolution? And what we find is that, first of all, when you look at the band structure, then you see that there's a lot of alignment of the electronic structure between the d electrons of platinum and the p electrons of carbon from the graphene. You can see that the peak positions are lining up, right? So what do we see when we look at the dissociation energy? What is the dissociation energy? It's the energy required to remove one platinum atom from a surface. And now this could be a platinum that is by itself sitting on graphene, compared to platinum from one layer of platinum on graphene, or platinum from a bilayer of platinum on graphene, and similarly platinum from a bulk 1-1-1, or platinum from bulk with a 1-0-0 termination. Okay, so what's the key result here? The key result is that the dissociation energy for the platinum being removed from 2 layers of platinum on graphene, that's the open triangles, you can see the open triangles here, is more stable than the corresponding 1-0-0, the energy required to remove platinum from a 1-0-0 termination, bulk platinum. So if you had bulk slab of platinum and it had the 1-0-0 facet, and you removed a platinum atom, you would need less energy to do that than you would to remove platinum from, that is a platinum 2 atomic layer thick platinum on graphene that had the same crystal structure, 1-0-0. Okay, and in fact it compares very well with the 1-1-1. So this was a big result as well, and this is was also published last year. All right, so then we essentially tried to do the structure on 3-dimensional graphene. So we essentially had these graphene foams that we generated, and do the deposition on the graphene foam, and we were able to then look at the the coverage of platinum and go all the way down to the atomic scale, and you can start to see on high resolution TM that we again have this 100 like structure, even though this is now very poorly defined graphene. It's not flat graphene anymore. And even in this case, we have this behavior. And what do we see? Well, we see chemically that the potential at which this reaction happens, the ORR reaction happens, depends on the material that is below the graphene. So if I look at the summary graph here, you can see that the overpotential, that is the reaction potential for the oxidative versus the reductive reactions, that difference, the smaller it is, the better it is for the catalyst in a fuel cell. And that value is smallest when we have platinum monolayers grown on graphene with nickel on the other side. And it's better than platinum on graphene without nickel, or basically with nothing on the other side. And as a control, we compared it to gold on the other side, and gold is supposed to make things worse, and it does. So we are able to get this electronic effect through the graphene in a real catalyst. So the conclusion that I would draw among all the different things that we've shown are two big ones. One is that graphene is a conduit for property tuning through it, and we've demonstrated this for catalysis. But what we imagine that's possible is that it can be done for electronic materials and magnetic materials as well. And finally, we have also shown that the platinum as a capping layer really strongly influences the stability of the catalyst. It can essentially make the catalyst corrosion resistant, permanently corrosion resistant. At least for the first 1,000 cycles, we didn't see any corrosion happen at all. So I'll stop here and I'll take questions.
Thank you so much, Dr. Alamgir, for this excellent talk. So now we can start to listen to questions. If you want, you can turn on your microphone and ask to Dr. Alamgir, or you can write in the chat. Thank you so much.
You're welcome.
Hi.
Okay, yes?
It's me, Martha. I have a question really quick. Maybe I'm not quite familiar with the LED deposition technique. Nonetheless, how can it be possible that you can control 0.3 units of monolayers? Is this has to deal with the number of cycles, or perhaps it has to deal with the reactions that takes place, and at the end you measure that this is the units of monolayers that you have of your platinum?
Is it possible to turn on my camera? I think you're controlling it on your side, Liliana, because it seems to.
No, Professor. Actually, everybody can turn the camera. I don't have any restriction.
Okay, okay. It seems like. Your question? I wanted to turn the camera on first. Okay, I hope you can see me now. Yes, so 0.3 monolayers. How can we get 0.3 monolayers? It is because we're using a self-limiting reaction. The details of this you can find in the papers, but essentially what we're doing is we are putting down a sacrificial metal, and that sacrificial metal in this case is copper, and copper will interact. And let's take the case of the gold as the substrate. Copper will interact with the gold such that every cycle, essentially, we can put down about a third, about 2/3 of a monolayer of copper, not 1/3, but 2/3. But then when we take that and we put it into a platinum solution, the platinum ions will galvanically replace the copper, and there will be two coppers removed for every platinum that comes down because of the difference in ionicity. And that leaves us with approximately a third of a monolayer of platinum. It's not exact, but what we do find is that after about 3 of those cycles, we get close to a monolayer in terms of the coverage.
All right, but then there's not a mixture of copper with the other metal. Then
no, the copper is replaced by the platinum. In this case, we do not see any copper remaining. So copper is an intermediary that is used as a way of decorating the locations where the platinum will go, and since platinum is more noble than copper, it
Yes.
essentially spontaneously replaces it. You can follow that reaction by watching that potential of that electrode, and that potential of the electrode changes and equilibrates to the electrode potential for platinum surfaces. Starts out as copper surface and then it ends up being a platinum surface. And when that becomes asymptotic, that's when you stop. And then when you do something like XPS, you don't see copper on the surface anymore.
Yeah, it makes sense. Also because it's too little. Okay, thank you so much for.
Yeah.
Thank you, Marta. So, someone else have some question for Dr. Alamgir? You can turn on your microphone, or you can write in the chat. Thank you. Professor, at this time, I want to ask you something. I want to ask you, how do you study the effect of the epitaxiality in a volume of your sample? Means you study by only transmission electron microscopy, or do you also do some kind of ABSD, for example, characterization of Paul figures characterization? Can you please detail a few more, please? Thank you.
The question you're asking is, how do we know about the epitaxial nature?
Yes, how do you study the crystallographic orientation of your field films? Thank you.
The crystallographic orientation is the direct way to do that is by imaging. You have to see it to know that it is. So, for example, the fact that it is 100 versus, let's say, 111 or 110, that is going to be very difficult to tell without having an image, because otherwise you'd have to use some property of the metal in this case, which changes as a function of which crystallographic feature or which crystallographic facet you have, and that difference has to be large enough. So one thing you could do is you could use the work function. The work function of the 110 and the 100 and the 111 are different from each other. But I wouldn't say that you would be able to get a pretty accurate measurement, because the work function difference is not that large, number one, and number two, you could have an average of different types of surfaces at the same time, and so you might get a value for the work function which is somewhere in between some numbers, and so then you wouldn't really know how the distribution of the surfaces are. So what for example, you wouldn't know that when it's one layer thick, it prefers to be 100, and versus when it's 3 layers thick, it prefers to be 111. That level of that level of information, for that level of information, you need spatial resolution and an imaging ability. So I would say that TEM is probably the best way. Now, the other part of your question is about epitaxy. Epitaxy means that you have a lattice to lattice interaction between these two materials. And in order to study that, you don't need to have an imaging tool. For example, I showed you this EXAFS, extended X-ray absorption fine structure results, where we are looking at the local atomic structure around platinum. And what we saw was that the platinum-platinum bond distance, on average, was getting shorter. This is that compressive strain that is imposed by the graphene. And that is only possible if the graphene and the platinum have a lattice-lattice interaction and you have epitaxy. Okay, so indirectly you get the information about epitaxy. The third part of this might be what you're asking, might be about coverage. How do you know that you're fully covering the graphene or partially covering the graphene and so forth. And for that, you could use electrochemistry. So you could look for a reaction where you look for a key reaction of the material that is underneath the platinum. If that key reaction shows up, that means the platinum is not covering that material completely. And we use that idea when we were looking at gold, graphene, platinum stacks. In that case, we could see the gold reaction when the platinum wasn't fully covering the graphene. Let's say a third of a monolayer or 2/3 of a monolayer, we could still see the gold reaction happening through the graphene. But once we got a monolayer and beyond, then we saw that the gold reaction disappeared. So that could be a way of getting an average understanding of whether or not you have wetting of the full wetting. So you have to use different tools, but if you really want to know spatial distribution of different types of crystallographic structures, your best bet is to do electron microscopy.
Okay, thank you so much, Professor. Someone else have some question for Dr. Alamgir? Okay, if there are no more questions, I only want to thank you again, Dr. Alamgir. Thank you so much for this excellent talk. We have learned a lot from you. Thank you so much. And I also want to thank every one of you. Thanks a lot for attending this seminar. We hope that you will join to the next activities of our student chapter, such as the weekly English Conversation Club, the next scientific seminars that we organize for you, among others. So thank you so much and have a nice day.
Thank you, Liliana, once again. Thank you to everyone for even in these difficult times and over this difficult medium for listening to my talk.
Thank you so much. It was our pleasure.
Bye.
Goodbye.
Thank you.